Hi, my name's Chris,
And my name's Darryl.
and this is our high-speed PCB design of the Cyclone 10 FPGA. So, in this section, this will be our overall design aspect. So, we decided to choose the bidirectional differential signaling rather than the single-ended or unipolar option. The signaling rate is of 1 gigabit per second. It's the most minimum that it can go, but it advertises to be around 1.43 gigabits per second. And the Cyclone 10 has about 188 GPIOs, which can be either a transmitter or a receiver in any instance. So therefore, it is bidirectional. So here we have a table from the datasheet where we were able to grab the differential output as well as the common mode output values to put onto our schematic. So here we could see that in order to reach a greater than 700 megabits per second, we had to have a minimum of 1 and 1.6 voltage in the input of the common mode. So assuming that we were going to get those kinds of values, we assumed we were going to get roughly around 0.4 volts in the output differential, and just to make it easier on the calculations, like a 1.2 right around here volts in the output common mode. So here we decided to go with the current mode option rather than the voltage mode option, and that's because we wanted a little less noise coming out of our or into the receiver. And for the MOSFET sizing, we decided to go with the 50 nanometer process because the VDD that goes into this diff amp or the comparator that we're using is 1 volt. That's roughly about close to what we need going into the chip. So they're very similar external voltages coming into the PCB. So here we have the comparator with the 50 nanometer process where when VP is greater than V of M, V out is equal to 0. So vice versa, if VM were to be greater than V out were to be 1. So when it's outputted out of this diff amp, we get like a unipolar result where it will either be a 1 or a 0 depending on what we just spoke about earlier of whether VP is greater or not. So the output voltage in our case was not attuned to our desired output result. We kind of wanted more of a 1 volt or a 0 volt type of option, but sometimes it would either go really low down to the 400 millivolts to 200 millivolts. But regardless, we were still able to get some form of correct result at the end of it. But as we reached our current driver, it got a lot harder to understand what was going on because it was just not functioning when we were working with it. We even tried putting a current source at the very top instead of, say, a MOSFET at the bottom or top to bias the current. We couldn't bias it past 1 milliamp, so we had to go without the current driver or voltage driver for the matter of fact. Fortunately, there is one good thing that came out of our design is that we were able to make it close to a homogeneous result where our parameters were close in relation to each other in terms of their resistance. So here we have a cross-sectional view of our PCB where we have the substrate right here and the line is going through the substrate down below at around 40 centimeters. We decided to go with the minimum of 40 centimeters just to get a feel for how our design is going. Here we have some connections here like in the ball grid array and our connection to our receiver. But because we couldn't get that driver to work, which it would be going up this way, but since we couldn't get it to work, we're just going straight down to the receiver. Otherwise, we do have a bunch of connections here that we can add into our schematic. So here we have the schematic version of the cross-sectional view we just saw earlier, and the transmitter's on our left. It's going to go through a bonded wire, then to the ball grid array connector, and then I put vias along the substrate just to kind of get an average going to involve more noise, just to see what kind of response our schematic would get. And then the PCB trace isn't just an ordinary T-line, it's actually a lossy transmission line where it actually allows you to input the inductance, capacitance, and the length, etc. onto this so we can actually measure the attenuation later. And then afterwards it will go to the connector of the receiver, and the receiver will receive that signal from there. We have the 2Z odd, which we calculated using the inductance and current that we found.
So for our timing system, we decided to go with the clock forwarding concept because of it is mesocronous, and that means that the transmitter and receiver will have the same bit rate and frequency as each other. It will also allow us to have a low to high frequency jitter tracking. However, there is a flaw. There are some limitations to having this concept, as clock skew can limit performance over time, and jitter can be amplified through the low pass channels. So for our Cyclone 10 U484 packaging plan, it comes with 484 pins as indicated by the number. 188 of those are GPIO pins, 70 of them are LVDS pins, 6 transceivers, and 264 signal pins. The rest of them are all power and ground pins. Taking the values of what we have in the packaging plan, we would plug it into our equations. To find out how many routing channels we have, we would plug it into square root 484 minus 1 multiplied by 4, and that would give us 84 routing channels. We know that there's only one route per channel because the spacing between each of the channels are too small. With the values we've gathered, we would grab those same values and plug it into this equation to find the quantity of layers for our design. By plugging in our respective values for signals, routing channels, and routes per channel, it would give us a quantity of 4 design layers needed. So the noise budget was a little bit of a longer, but also equally as important calculation for our project. Our transmitter and receiver offsets were about plus or minus 5% based off of our assumptions, and we also assumed that we had a receiver sensitivity of about 10 millivolts. To find the worst case reflection, we would plug it into the reflection coefficient equation, which is ZT minus Z0 over ZT plus Z0, to find the value. And we came up with the worst case reflection being about occurring at the negative 5% offset, which is approximately a 0.026 ratio. Of course, to have more accurate calculations, we also took into consideration the capacitive coupling, the inductive coupling, the reflection crosstalk, and the far end crosstalk. The far end crosstalk in this case is 0 due to us having a homogeneous medium. However, the capacitive coupling would have a value of 0.28, the inductive would have a 0.028, and the reflection crosstalk a ratio of 0.0138. Due to our voltage swing being about 800 millivolts, we could assume safely that our gross margin would be about 400 millivolts. Adding our worst case reflection and crosstalk reflection together would give us our noise coefficient of 0.0398, or Kn. We would then take this value and multiply it by the voltage swing, and this would give us our intersymbol interference, which came out to be about 31.84 millivolts. Taking all consideration of all the values we've calculated up to this point, we calculated that our bounded noise to be approximately 121.84 millivolts. Subtracting this from the gross margin of 400 millivolts, we have a final net margin of 278.15 millivolts. With this value being so small in comparison to the gross margin of 400 millivolts, we can kind of expect our signal to be more clean than fuzzy, for lack of a better way to put it. However, our noise calculations are not done there. We still need to calculate Gaussian noise. We would assume that we had a 5 millivolt unrelated backplane noise, 10 millivolts added Gaussian noise from termination resistors, perpendicular crosstalk, and other symbols in the design. But what about thermal noise and power supply noise? Let's talk about thermal noise. Our thermal noise equation is the square root of 4kTBr, and K standing for Boltzmann's constant, T for temperature, B for bandwidth, and R for resistance. We wanted to probably put this in the realm of room temperature, so we chose to go with 293 Kelvin. Our bandwidth was obviously 1 gigabyte per second, and our resistance about 100 ohms. Putting this into the equation, our thermal noise came out to be about 40 microvolts, which is completely negligible compared to the other Gaussian sources. The last thing we need to calculate in terms of Gaussian noise is the power supply noise. This is defined as the difference between local voltage references of the driver and the receiver. For our design, we can approximate that it is about 20 millivolts in design. Taking all Gaussian values we have up to this point, we can now solve for the root mean squared voltage. The root mean squared voltage equation would be, plugging in values, would be the square root of 5 millivolts squared plus 10 millivolts squared plus 20 millivolts squared. We can ignore the 40 microvolts from the thermal noise because it's negligible. You can then take this to a step further to find the signal to noise ratio voltage, which is the net margin voltage all over the root mean square voltage. That would then result in a value of 12.15 here, given here by the table. Plugging this into the bit error rate equation, we get a value of 9.15 times 10 to the negative 33. This value can then be used another step further in order to calculate the mean time between failures, which is the inverse of the bit error rate all over 1 gigabyte per second, which gives us a final value of 3.456 times 10 to the 15 years per error.
This is going to be the power and cost portion of our design. So when we measure power on LT Spice, what we can do is we can multiply the current with the voltage with VDD, so we could see how much power is getting drained, or rather dissipated, from the VDD source. But we also did it on the differential voltage to see how much on average was getting dissipated from that. So what we found out was that the differential voltage source was dissipating 977 microwatts on average, whereas the receiver's VDD was dissipating 112 microwatts. So this means that in combination we get about 1.089 milliwatts together in total. So therefore, total power multiplied by the 70 channels that we will have is 76.23 milliwatts. For the cost, we decided to look into the 484 ball grid array Cyclone 10 packaging, which was roughly around $135.50. And then the cost of the comparator was roughly about 53 cents, but then of course multiply that by 70 of them. And then for the PCB board for 8 layers with the whole area into account, 19 millimeters on each side, we would get a total cost of 184.71. For this section, we'll be talking about the timing budget. So within the timing budget, we have a rise time of 196 picoseconds, fall time by 144 picoseconds, and a minimum aperture time of 177 picoseconds. And this shows that the rise time has a larger amount of delay than the aperture time. So therefore, you'll see that the waveform kind of looks almost like a sine wave because it goes over it like a hump, because there's a very small amount of aperture time.
For the jitter, you can ignore the references to tables. These jitter values were given to us by the data sheet. With clock period jitter, the cycle-to-cycle jitter, and the duty cycle jitter all being equal to negative 40 to 40 picoseconds long. These particular three are under the DDR3 protocol. The transmitter jitter is about 200 picoseconds.
This is for the performance and justification of our results. So here we have a couple diagrams here, where the first one on the top right is our eye diagram, and we can see that it has a nice clean eye that we can visibly see. And on the bottom right is the transmitter, and then just before the line and the receiver from the top to the bottom of that same image, we have it's kind of like a smooth input into the receiver.
Because our design is also in a homogeneous medium, this is why we have a low reflection rate. However, this does not mean we have no reflection at all. It does mean, however, that on the far end, since it's a homogeneous medium, it's negligible and can be considered zero. We also noticed that we had a good bit error rate and a mean time between failures.
So even though we do get that smooth input coming into the receiver, we do get a minimum aperture time that's far below than we were hoping for. And this is going to most definitely affect our output. So our voltage swing has lowered a lot more than we anticipated as well. And it might be due to the fact that we don't have a current driver. So it's not providing enough current as it goes through all the parasitics that we've provided in the schematic. Also, in order to get a more cleaner looking eye, since we don't have any canceled skew rates, all of the skew rates are uncanceled in our system. So for our future improvements, we were thinking about using different types of processes within our driver so we could see if we can get a different, more better looking result, test different behaviors, characteristics of these different processes.
We would also like to try and increase the net margin because I know how much the net margin would affect bit error rate as well as the mean time between failures.
And then we'll create control loops to help reduce that noise or improve the signal's eye so that way the skew that happens at the very beginning that's actually not touching the very top like we would hope it would, to make it a cleaner eye diagram. Maybe we would be able to fix that by making those control loops within our system. Thank you so much, Dr. Harris, for teaching this class. It was a very rigorous class, but I was very interested all the way to the end.
I wanted to say thank you to Dr. Harris. This class was very insightful for me. I actually didn't think I'd be taking a grad level class for my undergrad core on the final semester of my college. It's been quite humbling, to say the least.
And doing this project made me realize that there's so much that goes into making high-speed design PCBs. I feel like there's so much I've left out or I haven't even thought of while doing this project with Darryl. It was very insane, but I loved it.
I feel like there's a lot more opportunity for both of us to actually learn more. Considering like this was something we never thought was a thing. We didn't know about systems not being ideal like this, where traces could be doing reflections. We always just treated things as ideal since 220, and this was just eye-opening for us.
Thank you so much, Dr. Harris.
Thank you.